All right, now here we are going over the final chapters of this whole semester. We will be introduce everything that is related to the technique, which is called Laplace Transform. This is going to be a very exciting and useful skills to get, and it will be the ultimate tool to solve linear differential equations analytically. We will see this one will be able to handle every single cases we talked about before, plus this one will be able to handle a lot of cases we cannot do before, which has actually a lot of applications in real life. All right, so let's first briefly introduce the idea of Laplace transform. The definition is given by the Laplace transform of a function ft. So we take a function, we transform it into another function. It's defined by L, we put a bracket, indicate this is a transform, f equals the integration from 0 to infinity ft e to the negative st dt. When you finish, you should receive, if you think about it, this is going to be a variable t, this is going to be a variable t, you have a starting and ending points. The final thing will give you some function, but this time with respect to the variable s, because t will be gone after you do the integration. So this is going to be transform a function of t into a function of s. It may seem weird at first, why are we doing this? But then later we will quickly show that this becomes super useful because of some nice properties this one has, especially when it is dealing with the derivatives. All right, so let's try some examples. Let's take the easiest function we have. Let ft equals 1. Therefore, we have a function which is called 1 times e to the negative st dt. And then the answer is going to be negative 1 over s e to the negative st. You may want to write down this, but then you realize, okay, you cannot do that, but you can do it by the limit notation. So that's how we do this. After that, what we have is, it's going to be negative 1 over s limit a goes to infinity 1 over a negative e to the negative 1 over s e to the negative s a minus, if you plug in 0 for t, which give you minus 1 over s. Together, you can see this one goes to 0. The one on the right gives you 1 over s. So therefore, this one is going to work if your s is bigger than 0. The reason is because you want this part to converge. And in order for this one to converge, you need to have something 1 over e to something. Eventually, this one goes to 0, okay? And then your s has to be positive. Otherwise, if your s is negative, clearly this one goes to infinity, so this one does not converge. So we find the Laplace transform of 1. A function 1 is going to be 1 over s, for s bigger than 0. Okay, now that's pretty nice. Let's take another example. Okay, let ft equals e to the 2t. So what do we have? We have L e to the 2t equals integration from 0 to infinity e to the 2t times e to the negative st dt, which is then we realize, okay, this is nothing but negative 1 over 2 minus s e to the 2 minus s d. Okay, again, we want to check what's going on with 0 and what happens at infinity. It's pretty easy to see this is going to be limit a goes to infinity negative 1 over 2 minus s e to the 2 minus s a minus 1 over 2 minus s. Okay, so if you think about it, it's going to be hold on, what do we have here? We have this. think 2 minus s, 2 minus s. There's no negative. Okay. T. 2 minus s. That's it. Okay. Now what we have is we want this one to converge. Then the only chance we got is we need to make this part negative, right? That means this one is going to be 0 minus that. Let's simplify a little bit. Switch the order with the negative. And this only works when 2 minus s is less than 0, which means this only works when s is bigger than 2. Okay. So L e to the 2t equals 1 over s minus 2 for s bigger than 2. So at least we were able to find the Laplace transform of the super easy function y equals 1, and also a relatively simple function, which is the exponential. We find, okay, that's what we got. From here, you can see following the same logic, we can actually do this for any number. It doesn't have to be 2. It can be 3, 4, 5, 6. If you change this to anything which is a, for example. Actually, why don't we just leave it as an exercise? Repeat what I just did with exactly e to the 2t. Try to do e to the at, where a can be any number, and it's very easy to do. Just follow what I just did, and you will be able to see it's going to be s minus a, and your s needs to be bigger than a. All right, so this is going to be how we do Laplace transforms. We take a function, we integrate it, we times it with e to the minus st, integrate it with respect to t from 0 to infinity, and then finally, we end up with a function of s. You put in a different s, you got a different number, comes out. So we transform the one function into another function. All right, that's the Laplace transform. What about other stuff, like L sine t, maybe? Okay, maybe L t square, things like that. We have all kinds of Laplace transforms, and all you need to do is just try to do the integration. For some easy functions, we can show that it is doable. You can find a detailed table online. But how did they get the table? They just did the computation for once, and because they were used frequently, so they actually put the tables online. You can do that. And finally, some assumptions we need to make. We were doing the integration from 0 to infinity, ft e to the negative st. Okay. This is going to be an improper integral. As we have done, we need to take the limit for the right endpoint. And if you recall what you had from calculus 2, it is very easy for this one to be not converging. So we need to talk about convergence. Do we have something finite? Okay. Then we need to assume a very basic assumption. That is, we cannot do it for any kind of functions. We need to make sure at least if we take the integration from 0 to infinity, this one does not give us something which is ridiculously big, like approaches infinity or negative infinity. The good news is, even though your ft can be really big, but we know that t to the minus st is going to be super small because it exponentially decays to 0. So if you take ft equals t squared, which goes to infinity as t goes to infinity, but you have t squared times e to the negative st, which is this. And you can see if your s is positive, this one is going to dominate whatever polynomial you put on there. So everything about polynomial is okay. Therefore, as long as your ft is not ridiculously big, it's going to be fine. So through the chapter, let me write it clear. Through this chapter, we'll assume ft is at most exponential. That is, ft is less or equal than e to the mt when t is bigger than k. That means your ft can grow exponentially up to a point, capital T, and after that you're below this. So you can have very huge upper bound, but as long as it's less or equal than exponential e to the mt, e to the negative st eventually just dominate what you have here because it's exponential decay. They cancel each other, and this t keeps going, but this t stops there. Okay, so then eventually this one is going to converge. It's going to become finite. Therefore, we can do the Laplace transform. All right, so that's everything we know about Laplace transform so far. As long as your function is nice, which means it's at most exponential, we can calculate it. Okay. Now we want to talk about why are we doing this? And we're going to use it to solve differential equations. Okay. Before we show you an example, now we want to actually check why this one is useful. It is thanks to its property of Laplace transform. Okay. The first one is linear. What we mean is L F plus a G or minus a G equals L F plus LG. L, a scalar times F is going to be a scalar times LF. This is what we call linear. So if you have something which is a linear combination of several functions, you can actually do the Laplace transform on each individual function and then do a linear combination after that. Okay, so that's the basic property we need, and it's very easy to prove. If you have 0 to infinity f plus g e to the negative st dt, of course you can split it into f alone, g alone. Okay, similarly you can do it with the constant multiple. It's pretty easy to verify. So I will put it here. This is important. Oh, my drawing may not be the best. Okay, this is very important, and ideas are here. Because of the property of integral, you can easily take the constant out. All right, linear property, that is okay. The second one becomes super interesting. That is if you know the derivative of a function. Let's just use y prime, because we will have those kind of things in the differential equations, right? So if you have the derivative of y prime, what's going to happen? Well, let's do it. That is fine. Okay, that is going to be, now remember what we had before. We have integration by parts, right? We can actually do the integral like this. To stay out of confusion, let's make sure that we're talking about t. Okay, and we're talking about what's this? Yes, minus the derivative okay, this is done by integration by parts. Good so far. All right. Now we need to focus on this. What do we have here? Let's plug in A. Let's plug in 0. Note, y is a function of t, so at 0 it's y0 times e to the 0, which give you just y0. Okay. Minus. Now we have this. We can change it to be plus s, because s has nothing to do with t. We can take it out. We have this one. Okay. Now this goes to 0. Why? Because we said y is at the most exponential. Then you cancel it with a negative exponential. So as long as for s bigger than 0, this is going to work. Okay. So this is going to be 0. What we have is minus y0. Okay. from this first term. And now we want to move this one to the front. And can you realize what it is? It's just the Laplace transform again for y. Okay, of course, this one only works for s bigger than 0 with some restrictions. All right. Integration by parts give us some interesting calculation, but then we can write down this property. And you can see this is really nice. Why? Because y prime is gone. That means if you're trying to do a differential equation, once you apply Laplace transform on both sides, the derivative won't be a problem. It won't be anything harder than Ly. Okay? Even y prime prime will be, later we will show, gone. Actually, any derivative of y will be gone, leaving you only Ly. Let's see example really quickly. Okay, so we have linear property, and we have linear property and also the derivative property. Now let's consider an initial value problem. Okay. Let's take the most easy one. y0 equals, let's do, I don't know, 5. All right. It's very easy to see that the answer is going to be y equals a constant, but we can plug in the initial value, e to the negative 2t. This is based on what we had before. But now let's solve it using Laplace transform instead. All right. So what do we have here? Well, what we have is step 1, apply L, Laplace transform on both sides. Good so far. All right. Now on the right-hand side, linear property, you can take the negative 2 out. So this one becomes standing alone term. All right. On the left, use the property of derivative. y0. And do you know y0? It's 5. Okay. Now what do we have? We have an equation. This equation has only one unknown. That unknown is called the Laplace transform of y. This one is your unknown. Therefore, what you can do is you can move everything from this side to the other side. We have s ly plus 2 ly equals 5. We have ly equals 5 divided by s plus 2. This is going to be your solution of ly. Note, in the whole process, we are supposed to handle the derivative, but thanks to the property of Laplace transform, after you do this, there's no derivative anymore. What's left is only ly. So that's almost like you have an algebraic equation. Don't worry about the derivative, and you can just solve it using algebraic operations. And eventually your answer is going to be ly equals something. Ly is going to be something which is a function related to s. So far, it has been done. It's solved for ly. What's missing is, of course, if I know the Laplace transform of some function, can I know the function? Say, if I know ly, can I tell people y equals what? Because if I can, I end up solving this differential equation. I'm just one step away. That, of course, gives us a very interesting idea. That is, if you know y, you apply L. Okay, you get ly. And if you know ly, can you apply something to get y? That should be something called the inverse Laplace transform. So that's going to be the second part we want to talk about. So number 1, what's the definition? Well, before we do it, we need to ask, is this one invertible? The answer is yes, it is invertible. Okay, which basically means 1-to-1. You cannot have two different functions. If you do the Laplace transform, they go to the same function. No. So the key here is to tell you the inverse is unique. Okay, so this is just a general way to say some function is 1-to-1, or L is 1-to-1. Which means you will not have Ly1 equals Ly2. And if that happens, then y1 is the same as y2. You cannot have two different function goes to the same Laplace transform Ly. Okay, this will never happen. It's 1-to-1. So it's invertible. Second, then you can just do the definition. LF equals Fs is the same as saying L inverse Fs equals F. In other words, if you take the Laplace transform, you got something, and then if you see this thing, you can backtrack Laplace transform, which means you can take the table from what we had before. And use it backwards. For example, if I know L e to the at equals 1 over s minus a, then automatically I know L inverse 1 over s minus a equals e to the at. So I can use the table from the left to the right or the right to the left. Really depends on, are you talking about L or are you talking about L inverse? Okay, so we can do it. Number 3 is, of course, it is linear. Let's be more precise. L inverse is linear. It's in the same spirit of L is linear. So the inverse is doable. Okay. So finally, with all of this setup, we assume the at most exponential for our function. We assume we had linear properties and the derivative properties for L, and then we have the inverse Laplace transform. Finally, we can solve initial value problems using Laplace transform. Okay, so let's finish this problem, but this time let's write down the full solution. Okay, formally. L y prime equals L negative 2y. For linear property, I can take the negative 2 out. For derivative property, I can take the derivative out, add s, and add initial value. Okay. This is 5 from the initial value. Let me put it here to highlight what's going on. And then what we can do is we can move everything with Ly on one side, 5 on the other side. Therefore, your y is going to be L inverse 5 over s plus 2. The only thing left is just can you do the L inverse? Now, the first thing we want to do is we look at this. So far, the only thing we know is e to the at goes to 1 over s minus a. And from here you can see that means e to the negative 2t goes to 1 over s plus 2. That's exactly what you want, s plus 2. Okay, so it's almost there, but you have a 5 here. But then you realize, well, thanks to the linear property, I can take the 5 out. And if I have this, it's exactly the same as what we had before with a equals negative 2. Therefore, this equals 5 e to the negative 2t. Why? Because L e to the negative 2t equals 1 over s plus 2. Therefore, the inverse Laplace transform, of course, give you this. We just solved the initial value problem. This time, we didn't guess, we didn't do separable equations, we didn't take any integrations. We just did a very simple Laplace transform, use the linear property and the derivative property to get rid of the derivatives. The rest is just solving an algebraic equation. The harder part is actually doing the inverse. For this case, it's easy. Okay. Beautiful. All right. Second example. Let's try something harder. Okay. How do you do this? probably you need to use numeric integrating factor, because if you look carefully, this is going to be linear. You do y prime minus y equals e to the negative t 4 negative t. You take the e to the negative 1t integration dt, which give you this as your integrating factor. So it's doable. It's going to be a lot of work. But now, forget about it. Okay? Laplace transform. Good. Good. Property of derivative. Do you realize it's always the same? So nothing to worry about. Just write things down. Linear property. Take the 4 out, and do you know the Laplace transform of e to the negative 2t? That's going to be 1 over s minus minus 1, which is 1 over s plus 1. We just did it. Okay. Now what we want to do is, Ly is here, Ly is here. Let's move them together. Okay. y0 is 1. Use the initial value. Then this is nothing but 1 minus 4 over s plus 1. Then Ly equals 1 over s minus 1 minus 4 over s plus 1 divided by s minus 1. So like we said, this is done. We used algebra. We didn't use anything related to derivative. Now the final thing is just, can you do the inverse of this? And from here you can see, well, at least for the first one I can do it. And thanks to linear property, I can do them separately. All right, this is e to the t. Okay, because again, e to the at goes to 1 over s minus 1. This is the same as a equals 1. Okay, this is going to be trouble. 4 over s minus 1, s plus 1. Okay, how do we do the Laplace inverse Laplace transform? We want to transform it into something we know. Okay, the 4 is not a problem. By linear property, you can always take it out. So the number on the top is not a problem. The problem is on the bottom. If it's this, I know this one goes to e to the t. If it's this, I know this one goes to e to the minus t. But it's these two multiplied together. And you really want them to be separate. You want this one and this one alone. Do you realize we have done this before? It's going to be partial fraction. That's what we did in calculus 2, right? We can actually split this one into s minus 1 and s plus 1, maybe with a constant on the top. The good news is, number one, constant doesn't matter because we do have linear properties. Okay. Second, once we split them, the first one goes to one Laplace, inverse Laplace transform we know, and the other one also does the same thing. So we can simply just split them. I will skip the part. You can do it yourself. Okay, but you can check my work easily. Then what we have is partial fraction, 2 of this. Oh, I don't have to rewrite it. Then what is the Laplace transform? An inverse transform of this. Well, it's going to be 2 because of linear. The first term goes to e to the t. The second term goes to e to the minus t. So finally, you have minus e to the t, these two combine, plus 2e to the minus t. That is your solution. Again, we didn't use anything, we don't have to memorize Before it was separable, this one was linear, so we use integrating factors. Maybe we have some other situations, maybe guessing the solution, maybe eigenvalue, eigenvectors, whatever. Okay, but for now, you don't have to. All you need is try to apply Laplace transform, and after that, all the derivative will be gone. The only term that you don't know is going to be Ly. Solve it using algebra, have Ly, then a lot of your energy will be focused on how to do the inverse transform of Ly. The good news is, we do have a table. We do know a lot about the Laplace and the inverse Laplace transform about the regular functions, like exponential, sine, cosine, maybe later. Okay? And the good news is actually, everything we solved so far either involves exponential or sine, cosine. Never tangent, never something weird, right? So far, at least every cases we had before, as long as we know the Laplace transform of exponential and sine, cosine, we will be able to do it. Okay, so this is the first lesson about Laplace transform. The key takeaway is probably the following. Later we will try, of course, more complicated case. The first one is it solves initial value problem. And the reason, let's see this. The first one is you need to know the definition. Second is you need to memorize this or know how to do it, but this is very important because we see exponential so much. Okay. Number 3 are the linear properties of Laplace transform. So we can do any operation we want. This may tells you that we can only handle linear ODE. For nonlinear, not our concern. Number 4, this very, very, very important property, which will get rid of the nightmare of your derivative once for all. And then, of course, because of that, because of this nice term here, you have to solve initial value problem. You cannot use it to solve general solution directly, unless you assume this one is going to be a general constant. That is doable, but just by definition for now, it is probably best suited for initial value problem. If you want to just solve an ODE, you need to assign a random initial value problem. That's where your constant comes from. So this can be used to solve the ODE, but in this chapter, we just focus on the initial value problem. All right. Probably the last thing is this one is tricky. You need to be creative. You need to do several examples until you see what kind of techniques you have. At least you can see partial fraction is something we will be using a lot. Okay, we will see them again and again in the future. All right, that would be all for the first introduction to Laplace transform. It's very useful, and it's going to be very exciting because we're going to introduce more and more interesting cases, which we cannot handle before.